Hello everyone. I welcome you to the day 19 of the training. I am so happy that you have made this far. I think you have constantly learned a few things about Verilog HDL, FPGA, architecture of a processor, and different IDE tools. Also, have hands-on experience with Xilinx IDE. Now, today I am going to discuss about some of the Verilog HDL scripts in the test bench returns. I'm going to explain about test bench, also some of the tasks in system tasks and also functional tasks. Let us go to the today's agenda. That is, we are going to discuss about test bench, and also we will see with test bench circuits like counter and pulse modulator. Most of the time in the architecture we don't miss any counter or we don't miss on pulse modulator. Hence we'll be discussing on functions, what are they required, and different type of tasks that we can write, and also the system tasks, how they are written, and what are the different types of system tasks, types of tasks. Hence, let us start with what is test bench. I'll go through each line by line to explain what it is mean actually. When you are going through the video again, you will be very familiar with this. Here, test bench of the Verilog HDL in the architecture development in the design of an FPGA. Test bench plays a simulation role where it is most important to check the functionality of the code that you have written. For example, you have designed something in Verilog HDL. You have a design.v file or design.vhdl file. For that, you need to check the functionality. How do you test that? You need to test it, right? For that verification, we will be checking with test bench. So test bench is nothing but it's kind of one environment that we create around the design or including the design, and we check the input and outputs, whether the process between input and output is working fine, or are we getting the desired output from the design that we have developed on the FPGA or the architecture. It's like virtual simulation. Simulation is like testing before implementation. For example, we run different types of simulations: functional simulation, behavioral simulation, structural simulations, timing simulation, and we analyze the entire design in terms of timing, performance, or the syntax, or any other things that are internal parameters of the FPGA architecture. So we'll be checking the entire design code, that is again Verilog HDL code. We will test and simulate that Verilog HDL code in a environment that is nothing but a test bench. In this is the major step in verifying the functionality of the design. Description, uh, design description, script through the simulation platform, and in terms of output waveforms. For example, you have a circuit of OR gate, and when you take a circuit of OR gate with two inputs and one output, what is the functionality of this OR operation? 1 or 1, you will get the output of 1. If it is 1 comma 0, your output can be 1 again. If it is an OR gate. If it is an AND gate, your functionality can be, if you have input values as 1 and 0, your functionality can be 0. What are we doing here? In the design Verilog HDL file, we are designing the logic circuits or the logic design, that entire architecture of the hardware. But in the test bench, we are assigning some values and verifying the output. Are we getting the same operations or same output at the given point of clock or reset? So that is called test bench. So waveforms are nothing but we will see the waveforms in terms of in this way. In the output, I'll show you with some of the waveforms in the later stages. And best way to learn this test bench or design Verilog HDL any example files is you can go to the EDA playground website, and in the EDA playground website you can register in it, and you can also write design Verilog HDL code and test bench to the same design file. And then we can check the functional simulation through the test bench. That is our main motto of the test bench. Then there are two methodologies in testing the Verilog HDL script of the design. One type of test bench simulation is test bench connected through the to the design and under testing. For example, you have a AND gate or some other memory element, memory module. You have a design file. What do you have? Design file. That is .v file. If you connect some additional hardware kind of thing, just imagine this is a simulation thing. Let us call it as test bench. And with this functioning, with this verification kit, your memory can be verified. So what is the functionality of memory again? In the last lecture I have explained, it is read or write memory. So you can do either of the operations. You can only read in the memory, or you can if you only read from the memory, that memory is acting as a storage element. And if you operate read and write operations in the memory, it can be a random access memory. So let us assume read and write are the operations of this memory. So if you connect a test bench, and if you have some write enable and read enable signals, command signals in test bench, like imagine some, these are the buttons here, these are the buttons here. If you click on write enable, you will be writing data to the memory here in the pile of registers. Or if you click on a button read enable in the test bench, let us assume we are playing through the memory. So whatever the data is there in the piles or stack of arrays, stack of registers, that can be read from the memory. Read means we will get the data to the data register and to the data output. Okay, so that kind of thing. And one another kind of test bench simulation is nothing but, now we are attaching test bench kind of verification script or verification module to the this memory design, this entire design of our primary design we are instantiating into the this thing. The second thing is having design considered in the test bench environment. Environment is nothing but whatever memory design you have. Let us call it as mem. Now this input output wires, input wires and output registers, all these are considered in an closed environment of test bench. So that is the most ideal case of using the same design in the inside test bench environment. So in the test bench environment, in a universal way, we have all these kind of input wires, output data collections, and whatever the hardware you collect here, that hardware can be bring into this test bench environment and can be tested in it. So that kind of thing. Mostly we use second kind of environment. We'll explain in the next lecture. So this is the method one, and test bench can be connected in to the design under testing. If your design is very small, like it is a multiplexer, or it is a AND gate or OR gate, any logical circuit or any other decoder or memory, simple memory device, that can be connected to the test bench environment, where it has all the values, and that values are sent through the device and collected at the feedback loop and got into this test bench. And you have a logic here in this test bench environment, and for this logic your device or design which is under testing can be verified in the test bench environment. So you are not disturbing any functionality here, and this is not enabled. So after you get the results, you will be verifying the comparison between input and output. And if you see the input and output are exactly the same, this input should tally with the output of this, and this output should tally with the input of this. Obviously these will be the same, and the architecture will be connected in this way. And coming to the method 2, having design considered inside the test bench environment. So you have a test bench environment design. So think it as design 2 and think your own design as design 1. This is a primary design, this is a secondary design. So in the secondary design, you are integrating your hardware. Whenever I say design, think of this as hardware. Okay, this hardware is internally embedded into the test bench environment. Got it? And now whatever this design you are thinking, now this will be similar to the primary design. So test bench environment design is now transformed into the primary design and verified in it. That is the meaning of design considered inside the test bench environment. So the Verilog module codes, Verilog code for test bench environment and Verilog code for this design, primary design will look similar when attached. And now if it is the same, the design looks, the test bench design looks same. Now whatever you test it here, the actual test will go through this design primary, right? So this test, if it is valid, and your primary test on the design will also be valid. So that is how we do it, and this is the most ideal way of doing the things. Let us now consider a few examples of Verilog HDL. So as I have said, I can take half adder design, counter, pulse generator. I'll try to explain memory design as well if we have a memory design, and I'll try to decode it. But yeah, I can give you good examples of these things. So let us take a first design of half adder. In the half adder, you can see module half adder. You can mention the half adder module and input and outputs as the second part, wire and reg third part. So for an half adder circuit, if you see, you have two inputs, two outputs, sum and carry. This is just half adder. You can have full adder as well. Full adder implementation with two half adders. If someone wants to do, just do it and let me know. And wire and register, sum and carry. This all inputs are wires, all outputs are registers, and always at the rate of inputs the procedural box starts, and begin and end you can write case. When you have inputs as 0 0, what is the sum? Sum is 0, carry is 0. If you have input as 0 and 1, sum is 1 and carry is 0. We are writing begin and end inside the case statement because we have two statements. That is the reason. And whenever the A and B are 0 and 1, you will be getting sum and carry as 0 and 1 and 0. And if it is 1 and 0, the same, sum will be 1 and carry will be 0. And 1 1, the sum will be 0 and carry will be 1. And by default, sum and carry will be at initial state, that is 0 0. And case, end and end module. Whenever you start it, end module. So this procedural block will be of 4, and if you want to mention case statements as 5, mention as 5, and this end module will be connected to the module. So this is how you write a design. So now you have designed the functionality of half adder from the truth table behavior, but we need to write test bench for it. So for the test bench, consider the design in the right side in the EDA playground, that environment in the website. You can see this module half adder and input outputs, whatever the design you write. But for the half adder, we have to give the inputs to test it. So module half adder underscore TB, we need to mention. There are no input outputs for the test bench. It is just an environment, so we don't declare input outputs, but whatever the wire you have written, that will be the register in this, and all the registers will be wires here. All the registers you have taken, that will be wires. Why? Because in the connections, if you see, Here the outputs of test bench are nothing but registers, but all the inputs to the design are wires. Understood? Likewise, all the outputs are registers, but those are inputs to test bench, hence those are wires. So whenever we write test bench, right, it is a definitive condition you need to follow, which declares whatever in the design you mention as wire, that can be named into register. It is a must and should be followed rule. That is a register, and register should be wire. Understand? Now I am explaining about the test bench. Our main area of focus for today's session is test bench, not the design. So registers and wires. And why did I use time scale? I'll let you know. Time scale is the one more thing, and here you should write the time scale as well. Whenever you write for the test bench, you need to mention in the design as well. So time scale statement, must and should. So then come to the instantiation. So first step is declaration. Second step, and this is a module. This is a half adder underscore TB. This is another module, another piece of hardware, TB, connected to the entire design, half adder design. Half adder design. So it is connected here in this way. Okay, relate it, imagine it. Then third step is okay, instantiation. So this is nothing but instantiation. So for this instantiation, why do we require instantiation? Because we are taking this design and we need to mention it such that whatever process we start or whatever testing we want to give as input and outputs, those will be tested to the specific design. So that is the reason we are mentioning it. We are just mentioning. We are mentioning means we need to label it. Label it means we have to instantiation. We have to instantiate. Instantiate in the name of module name. Okay, let me erase few arrows. Okay. So this is module name, and we need to give the label name, names, and whatever the input and outputs you have declared, that should be declared in the sequence. Okay, so this, take this only two parts, this name and input outputs including semicolon, take this and write it here and label it with a simple thing like every time we can use unit under test or design under test or label one, simply label one. See, design under test or UUT. You are taking this design and instantiation into this test bench environment such that whatever you tested here, that logical testing will be happening on the design. That's what test bench environment is created. So now you have done this. Let us come back to the green color. It looks nice. And you have to initial the process. So when you initial begin, why begin and end? Because we have many designs. So we have to give values to the inputs. What are the inputs here? Input A and B. So what are we doing? This process is tested here. We have just declared, okay, if A and B are 0, 0, if A and B are 0, 1, 1, 0, 1, 1. But here we are not talking about if. We are not imagining, we are giving. So begin your process in the test bench. After 10 nanoseconds, give the value a is equal to 0, b is equal to 0. Now we are assigning the values. We are giving the values into the design. Now a is equal to 0, b is equal to 0, a is equal to 0 and b is equal to 1, a is equal to 1 and b is equal to 0. So we have given into the design such that we have got these values at the output. So our desire is to get the sum and carry outputs after the test bench simulation. So a is equal to 1 and b is equal to 1. So we have given for this. What is hash 10? What is hash 10 at every statement? It states that in the beginning, after 10 nanoseconds, hash 10 is nothing but, I am repeating again, hash 10 is nothing but after 10 nanoseconds. After 10 nanoseconds, you start a is equal to 0, b is equal to 0. Then next hash 10 represents after 10 nanoseconds, means from the 11th to 20th nanosecond. So if you have a clock, very decent clock, we all will have clocks, okay? This is 0, 5, 10, 15, 20. What are we saying? For the first 10 nanoseconds, a is equal to 0, b is equal to 0. From the 11th, from this point, from the 11th to 20th nanosecond, you consider a is equal to 0, b is equal to 1. Okay. Likewise, after 10 nanoseconds, the third step, this is second step. I'm just explaining how the test bench Verilog HTL code functionality works like in the simulation, in the test bench simulation. So now after this 20th nanosecond, you will get the 21st nanosecond. Let us say 21st nanosecond. It will be very clear when you follow along. So 21st nanosecond till the next 30th nanosecond. Okay, in middle it is 25. Okay, 21st to 30th nanosecond, your values of a will be 1, b will be 0. Until the 40th nanosecond, after 4th hash 10, your values of a and b will be, you will know, just write it down here. I don't want to explain. Okay, then a is equal to 1 and b is equal to 1. I have explained. Okay, after 50 nanoseconds, monitor the display of the monitor. $monitor is nothing but a task, a system task to represent the output. So we need some display in the simulator. You execute the code and you will get the output, right? In the output window, you want some display. What is our display? Sum is equal to what? Carry is equal to what? So sum and carry are written in this way. I'll erase few of the things. And then monitor. This is the functionality to display the output. And sum and carry, and you need to stop it after 50 nanoseconds. You need to stop, just mention stop, and end the begin, end the process here, and you can write end module here. You can write end module. But why did I write this initial block again? So you already have an initial block. Why do I write an initial block again? This is to get the output waveform. Like all the output waveforms, you will be seen in the EDA playground that requires this kind of syntax, or in any Linux terminal you don't have any screen for testing FPGA connected to a Linux machine. If you run Linux OS on that, if you want to see the output in the Linux environment, in a server kind of environment where you will see the Linux machines, in that if you write these two things in the initial block, dump file and dump vars, in this dump.vcd will show the output waveform. Like I think I have given the example in this way. This is the output waveform. To see this output waveform in the EDA playground environment in the website, as I have shown in the initial classes, in that EDA playground website, you can see the output as if a is equal to 1, b is equal to 0, then what would be the output? Carry is equal to 0, sum is equal to 1. Got it? And if, see, this is not representing the entire A graph. This is just representing just one part of the half adder circuit. So now here A is equal to 0 until this point, until 30,000 picoseconds. It is 0. But after 30,000 picoseconds, 30,001 picosecond, it is 1. A is equal to 1. Then B is equal to 0 here. For that point, what is your carry? 0. But what is the sum? It is 1. Again, now A is equal to 0, B is equal to 1 here. Carry is equal to 0 again. A is equal to 0, B is equal to 1, carry is equal to 0, sum is equal to 1. So sum is equal to 1. Sum. This is sum. This is carry. Okay, this is B. This is here. So likewise, you can simulate. And B is equal to 1. And what is this? A is equal to 1. Carry is equal to 1. Sum is equal to 0. Why? Because you add 2 ones, you will get the sum as 0, but carry as 1. That is the half adder circuit. So now let us come to the counter Verilog HDL, and I will be explaining test bench for the counter as well. Next we will go to the pulse generator. Then for the pulse generator, after pulse generator, I will be explaining about test bench task, or I will explain the memory designs as well tomorrow. And test bench, half adder, module for the test bench half adder I have explained. Now counter, this is the design file, and I have kept the screenshot of this counter again from the EDA playground environment. Credits to those people. That was made by Dulos. And in that thing, go to the each line of the Verilog HDL code. You have seen the counter design many times. And part 1, to declare the timescale units, because in the test bench environment we are writing #10, #1, #500. This says after 500 nanoseconds, after 1 nanosecond, after 10 nanoseconds. That will be understood by the Verilog HDL EDA tools because of tick mark timescale. This tick mark you can enter by the one key press above the tab button. So tick mark timescale 1 nanosecond and 1 picosecond. So module, this part 2 declares module of input and outputs. Part 3, wires and registers. And simple counter design. If reset, output will be 0. Q is the output here, and it's a 4-bit output, but we are counting up to 15, I think. Now the counter has Q is equal to Q plus 1. I mean, this increments the value. This is a up counter. And end the module. For the test bench, what do we have to write? I think I have given best test bench here. I have just written in separate format, but you can see the test bench here. Test bench structure. You will be seeing the time scale units that is to be declared in the test bench environment, and declare the module for register and wires. Here registers are written in terms of test bench, but these are actual wires in the Verilog design. For example, in the design, remember, clock and reset are wires. This is design. Now come to the test bench. Clock and reset are registers. That's what I'm saying. Wires in the design. I'm writing just to give you some reference on it. And whatever the wires you mention here, those are actually the registers in the design. After that, you need to instantiate the design with counter and input outputs. And if you see the design here, you have mentioned counter, input and output of the design. So that you need to write down here with the label. Okay. Now the testing process begin by initial begin. So every time we have two blocks, I'm just recollecting or I'm jogging out of your memory. We have initial block, always block. So initial block sets the values of all the initial inputs that we need to give. Clock and reset will start the actual initialization starts at ground zero. Now I'm saying these are the zero values. Now this is clock, and I have okay, this is clock and this is reset again. Those are at 0. Imagine after 10 nanoseconds, what are you asking about? You are asking reset to be 1. So reset to be 1. But again after 10 nanoseconds, your reset should be 0. Reset to be 1. This is reset. And reset is equal to 0. Why reset has to be 0? Because at the reset is equal to 1, if reset is equal to 1, which runs if block. Let us go to the here. If reset is equal to 1, then only q is equal to 0 is working. So if block is working. Okay, yellow ruins our design. So if block is working, okay, else should work at reset is equal to 0. That is the functionality that we want to test in the test bench environment. So in the test bench environment, we are declaring reset is equal to 1. Then if reset is equal to 0, what happens? The design will be incremented. Q is equal to q plus 1. Design will be incremented. So if reset is equal to 0, else reset is equal to 0, q is equal to q plus 1. So else, now the reset is equal, runs the else block. Else you are running the else block. Now q is equal to q plus 1. This has to be displayed. Display it. $monitor, $time, colon, quotation marks, q is equal to %d. This is a kind of representation for the output, and comma q will be whatever the value of q you are getting in the else block, that q will be considered by the %d. Okay, %d decimal, and that output can be seen. So that output can be seen in this format: 0, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F. Then again count begins. Q and reset low. When reset is low, the actual counting begins. This is the test bench environment, but also for the design environment. In the design, else block runs with the 0, and after 500 nanoseconds, 500 nanoseconds means 5 lakh picoseconds, your design will stop, halt the output. And part 4 is to see the waveforms. So clock should not be clock, I mean this generates the clock. After 10 nanoseconds, clock will be stopped, like whatever the clock you see. After 5-10 nanoseconds, see, after 500 nanoseconds, this process should be stopped. Like this initial block will be ending here after 500 nanoseconds. But a clock, you need to stop at 5/10 nanosecond. That is what this definition is. Always this. And then initial block, this is to display the output waveform. This is mandatory, like we have done for half adder output waveform. This part is for output waveform. Hence, you can see the output like this. Don't forget to write end module for the test bench as well. When you have written module, immediately write end module. There will be only one end module, only one module in the declaration. Now let us go to the pulse generator. For the pulse generator, you can see design will be the same, and you have the inputs of clock, reset, Q, Q next, and pulse. This pulse is to represent the output. For example, inputs are clock and reset. Based on this, you are deriving the outputs Q and what is the Q next, just for the reference, and overall the pulse. And this pulse can be our new clock. Okay, that can be new clock, and this is our old clock. Our aim is to generate new kind of pulses, but initially we have a initial normal clock with same period. Hence, that is a functionality. See, module pulse underscore generator, like you can see this design as this way. So this module, you can see pulse underscore generator. I have named it as pulse underscore gen 3. It is a module 3 pulse generator with the clock and reset. I mean, for every 2 bits of data, for the third bit, the pulse will be generated. Pulse will be generated, and again it will be 0. Pulse will be generated. So you will see it in the waveform. Just understand, these are the inputs. For a pulse generator, you have clock, you have reset, you have Q, I mean that is the output here, Q, and you have Q next, and also the pulse, required pulse that we are getting. So this is the Q. Hence, we have declared input and output as well as the reg and wires. Whatever the inputs you declare, those will be the registers and wires, and wire pulse and wire Q next. Why did we mention this here? Because those can be in out modulus. Q next is this Q next. Okay, assign the values of Q next, how it is taken for the module 11 or module 3. If it is module 3, you can mention if Q is equal to 2. For example, I'll let you know. Take it as a module 11. So simple difference is you can mention as Q11, and output can be taken for 9 bit, and you can mention at 9, and for every this kind of generation you can see the output as for every 11 bit generations you can see as this. Okay, now where are we in the design? So whenever we want to write the test bench, right, check whether the design is proper or not. So now to give you an example of 11 modulus pulse generator, I have took these inputs clock and output Q and Q next with the pulse, and after declaration till this part, first part, second part and third part, you need to assign the values. This is the condition, basic condition. Like if you Q is equal to 10th bit, like 10th bit, likewise you have 10 pulses, you can go for the 11th or for the 10th, starting from 0. If you take for the 10th bit, the pulse actually generates, you will see it in the waveform. So if Q is equal to 10, is it true? Then it is Q next is equal to 0. Q next is equal to 0. It is 1. If Q is equal to 10 is equal to 0, then Q next is equal to Q plus 1. Q next is equal to Q plus 1. Okay. Likewise, for assigning of the pulse, Q is equal to 10. You can have, if it is true, pulse will be high. That is what we are declaring, right? For 10 continuous bits, if we see, for the 11th bit, you need to see pulse as high. Whatever the waveform you are talking, that should be 1. Now, if this is pulse should have a value of 1. That value of 1 we will be getting if Q is equal to 10. And at this Q is equal to 10, we are getting Q next as 0, because it has to be reset again. Until then it can be 1 or something incremented value. But at this Q is equal to 10, pulse will be 1, Q next is equal to 0. Or else if it is false, then the value of pulse will be 0, like this. So Q is equal to 9 or 8, Q is equal to 8, then pulse will be 0. Only if Q is equal to 10, I'll mention it again. Only if Q is equal to 10, pulse value will be 1, or else pulse value will be 0 if Q is equal to 8 or 9 or something not equal to 10. Just understand, assign the values like this. Then what is the procedural work? For every reset is equal to 1, initial value should be 0. Else if reset is not equal to 1 or reset is equal to 0, then Q next is equal to Q. Whatever the value of Q next is there, that will be stored into the Q. That will be given to the Q. So Q follows Q next. Okay, let us understand through the test bench. So for the test bench, you can see timescale. You can actually practice this in the EDA playground. You need to practice it. So how will you practice? Take this test bench and design Verilog HDL files and copy paste in there, or actually write them line by line, understand the functionality in the way I have explained, and go to the test bench, write the test bench in a same particular way, part 1 to input, process, output, all these things. So process will be the same. You can see the pulse generation. So whatever the wires you have declared in the design, those will be registers, and all the registers are wires now. I mean registers in the design, wires in the test bench. Wires in the design, registers in the test bench. So module, pulse generator, and initial block, it will be the same. After 11th nanosecond, make reset as 0, and as I said, after 11th nanosecond you can make reset as 0. When the reset is 0, what happens? Q will be displayed. Q will be displayed, but what is the functionality of Q? If reset is equal to 0, Q will be Q next. So Q will be Q next. So 1, that comes from this. Q is equal to Q next. Q is equal to Q next. So it follows. Likewise. So after 11 generations of these modules, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now here Q is equal to 10. Q is equal to 10. We have understood if Q is equal to 10, then Q next is equal to Q plus 1. I mean Q next is equal to 0. That is Q next is equal to 0, and pulse will be 1 bit 1. 1 bit 1 meaning is nothing but 1 bit binary 1 is nothing but, see, pulse is equal to 1. Q is equal to 10. Got it, guys? So that is how it works. So, but where are we starting now? We are starting at Q at 0 position. Now Q is equal to 0, 0th position. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So Q is equal to 10, and Q's 10th position. I mean Q's 11th position. So modulus 11. Don't get confused here. Now Q is equal to 10 when we declare from 0th position. Earlier I have been mentioning, likewise we have mentioning from the 1th position, and now it is 11th position. 11th position, but Q equal to 10 when it starts from 0, right? We are starting from 1, it is 11. We are starting from 0, it is 10. So when 10th pulse is equal to 1 bit 1, and Q next is equal to 0. As mentioned here, Q next is equal to 0 when Q equal to 10. Understood? That is how pulse generator works. Same as the counter. Okay. Now coming to the test bench task, we have very similar tasks. Test bench tasks have functions and tasks, and system tasks we have. Functions do return the single value. At least we will have some output after the function operation, but after the task executed, we may get the value or we may not get the value. Task is nothing but another block, like initial block and always block we write, right? Likewise, imagine like tasks are nothing but some set of operations. So task means that is to be executed, working, function. So some set of the system tasks you should know while writing Verilog HTML is nothing but dollar display. It is nothing but to display output. In example, we can consider this as a printf function in the C programming, and dollar monitor you can consider it as used for display when the change of the value. Monitor is nothing but it is a bigger function than the display. It displays all the times. In the monitor, dollar monitor, you can also include dollar time. So also output of the queue like this, like in the test bench we have mentioned, right? Dollar monitor, dollar time, quotations. In the quotations you can mention whatever the message you want to print, whatever the message you want to display. Like in the half adder we have declared sum. In the counter it is q, but in the half adder we have declared sum, right? Yeah, in the quotations we have declared sum and carry. Okay, likewise in the quotations whatever message you want to see, that can be written in the you can do two displays or display of two items in the monitor. So use the display when the change of the value, and for every change of the value you can monitor. So monitor is a bigger thing. Instead of dollar display we can write monitor, and dollar display only displays one single output at one point of time. But if you use dollar monitor, for every iteration of the test bench simulation you can see the output. You can directly monitor everything. And dollar stop is to stop the simulation, stop the functionality. Dollar finish is to stop the simulation completely. Here dollar stop you can restart it again. Dollar finish is to end the process, end the initial block or end the always block, end the task, any other thing. So dollar f open is to create file. So you want some input files to be tested on the FPGA architecture. So you can consider those input files into the test bench simulation, and then you can mention it as $f open. So you can create them or open that file and read that input data from that. So you can literally mention it. And $f close is to close the file, close the functionality. Close the file, stop reading from that file of the data. I'll give an example of input.txt file in the next class as well. So $f close is nothing but this is to close the file, and $f display is to print the data to the file. So whatever you display here, whatever data you get, you show the monitor file, you can log that data into the separate file. Sometimes in the industry while we are working we need some reference log files of the previous work to check the functionality, how better it has become. That is to be there. So sometimes we use $f display to write this. Don't get confused between $display and $f display. One single thing can change. $f usually represents the simulations of the files. So that is system task. And some other tasks are $random, $read mem. $read mem is to read and write the memory inputs. Like if you have a memory and if you want to write and if you want to read from the memory and to the write to the memory, you can always say when you have a file read mem h hexadecimal, read mem h will always do this task of reading inputs or writing onto the memory. $random is to generate a random value. $random will also be used in some of the linear feedback shift register applications that writing the design. $random is to give the random value, some decimal 8, 9 or some binary 10, something random values it will be showing. And $dump file, you always see this in the $dump file. Whatever the waveform is written, that waveform will be dumped into the .vcd file, and this .vcd file will be considered by the EDA playground, and that EDA playground virtual environment or Linux environment will consider the output waveform stored in the dump.vcd file, and it is exhibited, it is shown in this format. So $dump file is nothing but file name, this is syntax. This is to see the waveform and the value changes on signals in the simulation of the design. VCD value change dump file. Sometimes it can be asked value change dump file. Dump vares is nothing but whatever the level that you are talking about, and list of modules that you want to showcase in the dump output waveform files. So that is a system task, and this is FPGA architecture you can see. And if you have any questions, just let me know. I'll be here to answer everything. And thank you very much. Nice to see you all.